Yeah, good morning. So we have some additional problem for homework number 1. Okay, so first one. Okay, I need alright. Yeah, you can find it easily in a website, right? If you go to this website, see, you write the Korean character, you will see Chinese character. So this implies you can see it in the quiz, right? Because okay, all right. So any question? No. I think you will be you will get a lot of help if you understand the Chinese character. I mean, in near future. Okay, let's continue with chapter 1. So, today, 8 p.m., so there is a quiz discussion here. So, let's just say, Ponius, eh? So, here, okay? Yeah, we talked about some initial condition of a capacitor. See, in a capacitor, the displacement current of a capacitor can be written as C over dV over dt. So if I have initial condition here, then I can replace this one by this, right? So this is my voltage, and then I have I there. So this voltage is just the initial condition, right? Just the initial condition. Yeah, this can be replaced by just 1 over S, sorry, this constant. Eh? And then this impedance is just 1 over SC. And this capacitor is zero initial condition, right? Zero initial condition. Zero initial condition and initial voltage. It makes sense, right? So at the t equals 0, the voltage across those two elements is t equal, this value, Vt equals 0, right? Yeah, if you transform this differential equation, see, you can see so if you write Vs, this is 1 over SC IS plus 1 over SVT equals 0. Right? So it has see, a capacitor component with a zero initial condition, and in series with a VUT, right? This is only VUT. Okay. Yeah. So let's just see. Yeah, this capacitor. Yeah, this is 1 over SC, and then I have a voltage which is initial voltage divided by S, right? That's my equivalent circuit of capacitor. This is a Thevenin form. You can convert it into Norton form, right? In the Norton form, say, you can find the short circuit current. So in the Norton form, I may write it 1 over SC, and then current, right? Current. Which way does it go? If I short circuit this current, short circuit, yeah, the current should go out, right? Go out. Is it something like that? Yeah, I think the current should. Let's just see. It's a open circuit voltage, right? Current should go this way, right? This is V. This is I. Right? The current is what? The current is SC. Yeah, this current value is SC times VT equals 0. Okay, that's the current. Oh no, sorry, no S. Just C times VT equals 0. That's Norton form. But this one is more, easier to remember, right? Capacitor voltage, initial voltage in series with zero initial condition capacitor. Yeah, question? No? Alright, let's continue with the inductor. Yeah, this inductor voltage is L over di over dt, right? So this one, so inductor, the current is a state variable, right? So we can write this inductor. Yeah, this is a intuitive. So this inductor L, this L has zero initial condition, right? Zero initial condition. Yeah, there is no current in this inductor at t equals 0, right? And then, so in the entire current I is this current I t equals 0 at t equals 0, right? Because there is no current through this inductor. Yeah, so we can write this one like impedance SL, and then current in the Laplace notation. Okay, so this is a Norton form. if I write it in Thevenin form, should be like that. Open circuit voltage should be L times I t equals 0. Okay? Now this one is easier to remember, right? Okay, question. No? I think this is something wrong here. Yeah, it should be here like that. This is wrong again. Okay? Two wrong places here. Okay, yeah, we have two things to discuss. See, one person, before going into here, say, uh, yeah, my VST equal 1 plus 1 UT. Yeah, in this case, what's my VOT? Yeah, so my VST waveform, so it was 1 volt, and then change it to 2 volt at the t equals 0, right? What's the VOT in this case? Yeah, here see, for t negative, yeah, this is DC voltage. Capacitor is open circuit, right? Open circuit. So my VOT should be 1 volt. This is my VO. And then when it goes to 2 volt, it will go to 2 volt, right? Eventually. So we know the solution. Then how can we solve this one? Yeah, let's just try to initial condition. Yeah, initial condition. Say, I can put my initial condition here. Yeah, initial condition is 1 volt to UT, right? This is my 1 volt to UT. And then suddenly, this is a 2 volt, right? So we can make this is a 2 volt to UT for t equals 0. I mean positive t. Then see, my VOT is the entire voltage of this 0 initial condition capacitor and this 1 volt UT. Okay? Yeah, so if I use my Laplace transform here, so this thing should be 1 of S, right? So my VOS is just this 1 of S plus the voltage across this 0 initial condition capacitor. Okay? Now that's only what? That's only I know, the voltage drop between here and there is, see, if you see, it's only 1 of S, right? 1 of S times impedance divider. So, yeah, this one is just what? Hmm? I will multiply this C, then SC. SC. I multiplied SC. Okay, yeah, this is my VOS. So, after some manipulation, this should be so my VOT will be 2 minus exponential t T of RCT UT. So it's same as this one, right? Or T positive. Okay? So any question? 네. 그렇죠. 라프라스 변환에서는 항상 T가 그러니까 파지티브일 때만. 예. 저 사람 스피커가 안 되네. 크게 말해봐. 볼륨업. 이거 지난번에 했잖아. 요거 그죠? 요거로 바뀌었다는 거 아닌가? 그 전 단계요. 그건 이 부호는 요 전압 플러스 요 전압이죠. 그러니까 요 밑에 전압은 이렇게 돼 있고 그 위에 전압은 그러니까 여기에 걸리는 전압은 요 사이의 전압에서 요 RC 임피던스 디바이더 I가 같으므로 임피던스 비율이 되겠죠. 그래서 요 사이에 걸리는 전압이 얼마나 잤더니 2UT하고 마이너스 1UT 하니까 그냥 1UT가 되죠. 1 over X. 1 over X. 임피던스 디바이더. Okay, some of you may not agree with this one, but there may be some other way. Superposition. Okay. Okay. Superposition. See, this VST is actually 1 plus 1 UT. 1 plus 1 UT. Because see, it changes from 0 to 2 volt at the T equals 0. So I can decompose VST into two parts. One is DC and the other is just UT. If my VS is 1 volt, just DC, what's my VOT? This is DC, current is 0, right? Open circuit. So my VO should be just 1 volt. If my VS is just DC, right? Yeah, if my VS is just 1 UT, yeah, my VOT should be 1 minus 1 minus exponential T over RC UT, right? You can find it. So by linear, because this is a linear circuit, my VOT for the combination of those two should be 1 plus 1 minus exponential minus T over RCT, right? UT. So, yeah, this makes sense, right? So, for T equal positive, my VOT should be just 2 minus exponential minus T over RC, right? Yeah, we got the same answer, okay? By linear superposition. 에? UT는 1이니까 얘 T가 positive일 때는 UT가 1이죠. 네. Yeah, actually, one student asked a question about the homework. I mean, lab experiment number 1. Say, for example, I have RC and CR network here. Say, this is ground, this is my VS. Then I have same RC here. What's the relationship between this V1 and this V2, this relation. I think you already know that, right? Yeah, my V1s is VSS, this times, you can see this is, you will find it, right? My V2s will be VS times SRC 1 plus SRC, okay? Then what's the relation between these two? Yeah, I will divide V2 as V1 as, yeah, it's SRC, right? So, yeah, then you can see, oh, this is what? Oh, strange, 1 over S, eh? Oh, so, so actually, what's the DS of, see, for all the, I mean, the time dependence of all those variables contains the time dependence of exponential st, s equal derivative, right? Okay. So then in the time domain, my v2t should be rc times d over dt v1t, or any vs, right? Okay, question. No other relation. Hmm? No question. Actually, we used something. LC resonance, eh? Parallel connection of LC, RLC. Okay, no question until now. Okay, let's talk about the resonance circuit. Resonance circuit. Yeah, resonance. Resonance. This is 가틀공. Yeah, this is by resonance, right? Resonance. Say, if I have LC in parallel, yeah, the energy of inductor is linear inductor is this one. Energy of capacitor is this one. Yeah, I have some switches here. Some switches, maybe some current source or something like that. Let's see. Yeah, so this is my DC current, okay? DC current. And yeah, for T negative, I just connect this switch for a long time. So this is DC, right? So in the DC, oh yeah, I should add some more. Okay? You may not like it. This is DC. Okay, DC. Right. For the DC, time derivative is 0 because it doesn't change with the time. So, inductor current, inductor voltage is 0. capacitor current is 0, right? So capacitor open circuit, inductor short circuit at DC. So for T negative, inductor is a short circuit, capacitor is open circuit. Capacitor current is 0, inductor voltage is 0. So the current should be this I0. Okay, this is I0 at the T equals 0. The capacitor voltage is 0. Oh, sorry. Yeah, capacitor voltage should be 0, right? Because of inductor. Then I turn off the switch. Then what will happen? Yeah, I have energy stored in the inductor, half Li square, but there is a 0 energy here, right? Because the capacitor voltage is 0. Then next time, see, I know, let's see. So this is my current. This is my voltage. Because of inductor, the voltage will be L times di over dt. Capacitor, the current, this one is capacitor current, right? Because this is open circuited. So my capacitor current is C times dV over dt, right? So if I substitute here, say I will get this differential equation LC times similarly I will get same form of second order differential equation. I have two energy storage elements. I have a second order differential equation. Okay. Okay. So let us see. We will use the initial condition. See, there is no initial condition in capacitor because the capacitor voltage is 0. But this one, L has some initial condition, right? I0. So I will use the equivalent circuit for that. Yeah, that one is equivalent circuit is capacitor has this has 0 initial condition. I will divide L into 0 initial condition L and this I0 times UT there. Okay. So what's current I? Oh yeah, this is I, my current I. Okay. So this is my voltage V. Those two elements, C and L, this doesn't, this is a 0 initial condition, right? 0 initial condition. Zero initial condition. Okay, then see, I just replace this one by impedance, 1 over SC, and then SL, alright? Then see, how can I, this is just I0 over S, right? Because of UT. Yeah, what's my voltage? Yeah, my voltage Vs is just what? This current times impedance. What's impedance here? Yeah, that's sum of admittance. Yeah, this is my equation. Say, then okay. So this is what? Yeah, Li0, Li0. Just I0 over C times S square over LC, something like that. I think you can find yeah, this is C. For example, this is S. Yeah, what's transform this one? Yeah, see, S square A square over A. Yeah, this translated to cosine AT, right? Is it right? Cosine AT. Oh, sine AT. Sorry, it's a sine AT. If this is S, it's a cosine AT. Then see, I need a square root LC here. Say I need a square root LC there. I will multiply square root LC somewhere. Then this is only my sine. Yeah, so this is LC. Yeah, this is I0 square root LC something. Yeah, this is my VT should be sine T over square root LC. Okay, UT. Yeah, you can find the IT easily. Yeah, IT is nothing but minus IS 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 equal minus IS times oh no VS equal minus IS times 1 over SC, right? Yeah, you can find this one. So is it 1 over SC? Yeah, I think this is 1 over SC. So anyway, my capacitor voltage T, and my capacitor voltage was 0 for T negative, and then it oscillates, right? Keep on oscillating, right? My inductor current, I'm not sure exactly. My inductor current will change some 1 amp and then something like that. So if you compare the sum of energy should be same, right? They just exchange energy with each other. Question. Oh yeah, you're right. L and C does not dissipate energy, right? Yeah, if I have a resistor here, say it will be attenuated, right? Attenuated. Okay, any question? No? Okay, let's talk about some spice. I think you familiar with you should be familiar with the spice, right? Because of lab. Yeah. So this is some RC filter transient analysis, right? That tran has something like say here 1 microsecond, 10 millisecond, 0, 1 microsecond. Yeah, this means this is a printer step, and this is final time for simulation, the ending time for simulation. This is start time for printout, start time for printing. And this is a max time step, max internal time step in SPICE, inside the SPICE. So SPICE uses some sort of modified nodal analysis, and then it adjusts its time step by itself automatically by calculating change of some state variable, inductor current or capacitor voltage. Then see if I make it very tight, the accuracy improves. Okay, any questions until now? Yeah. 프린트 스텝이 뭐냐면은, 여기 시그마 스페이스는 잘 안 나올지 모르는데, 그러니까, 닷 프린트 트란 V1이라면은, 이제 V1, 찍어보면은, T1, V1, T2, 뭐, V1, 2, T3, V1, 3, 이렇게 하는데, 요 프린트 스텝이, 요 프린트 스텝, 그러니까 0, 1 마이크로 세컨드, 2 마이크로 세컨드, T2가 2 마이크로, T3가 2 마이크로 세컨드란 말이죠. 그게 프린트 스텝이에요. 근데 그게 인터널 타임 스텝하고는 같지가 않죠. 예? 자기가 인터폴레이션 그렇게 해가지고 만들어주는 거예요. 속에서는 좀 다르게 계산해요. Okay, let's move to op-amp circuit. Operational amplifier. Yeah, this op-amp see, operational amplifier say for circuit analysis will assume ideal op-amp. Yeah, in an ideal op-amp, the voltage gain is positive, very large, right? Voltage gain is very large. So here, see, this is a VI positive, VI negative. So my the op-amp characteristic is like that. So the voltage between this output node and ground is voltage gain A times this differential input voltage. Okay, differential input voltage. Differential input. Yeah, so it's when gain A is positive, I mean infinite. Usually ideal op-amp gain is infinite, right? So we use mostly feedback. Feedback means my output, say, for example, yeah, we apply this output to input, right? That's a feedback. In a feedback, say, yeah, this VO should be what? VO should be this VI. This is V epsilon. Yeah, this VO should be minus A times V epsilon, right? So this is finite, 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 right? This is finite, finite. And this is infinite, infinite. Then this should be 0, okay? Because gain A is infinite. The V epsilon should be very, very small. We just assume it's 0. So this happens with a negative feedback, okay? Negative feedback. See, I apply VO to minus input. That's a negative feedback, right? So if I have a negative feedback around the op-amp circuit, I should have a virtual ground. The virtual ground means see, my VI positive input is same as VI negative input. Yeah, so let's look at it more closely. See, in a amp gain is very large, huge, very large. A is huge, very large. See, so here see current is 0, right? The current input is 0. So my Vx, for this Vx, I have two sources here, two voltage source, Vi to ground and Vo to ground, right? Then, see, by using linear superposition principle, I can calculate the Vx in terms of Vi and Vo, okay? Because the current through this one should be the same, because this op-amp current is 0. So then if I make a Vo equals 0, I can get this equation, right? If I make a Vi equals 0, I will get this equation, okay? So, yeah, then see, I know the amp characteristic. Amp characteristic, see, this is Vi positive is 0, and then, so my amp characteristic will look like that. So see, this is A. If A is large, it should be like that. So I assume A equal infinite. Then my op-amp characteristic look like that. Because of supply voltage, it's limited, right? This is supply voltage limit. The gain is infinite here. That's the op-amp characteristic. How about this characteristic, R1, R2 characteristic? So this is Vx, this is Vo, right? Yeah, so see, I can write this Vo in terms of Vx, right? My Vo should be what? R1 over R1 plus R2 Vx minus R2 Vi, right? So this Vx relation depends on this Vi value, right? If Vi equals 0, I will get this curve. So operating point is here. So in this case, my Vx equals 0, and also my Vo equals 0, okay? When Vi equals 0. Now makes sense, right? Vi equals 0, this is a 0, this is a 0, this is a 0. Oh, no problem. Yeah, when Vi equals positive, so this one become Vi is positive, what happens? Yeah, my curve, Vo curve should be like that, right? This is Vi positive. So operating point is here. Again, Vx equals 0, virtual ground. My Vo should be what? See, I know Vx equals 0, right? My Vo should be minus R2 over R1 Vi, right? So my Vo is negative, okay? Okay, anyway, because of negative feedback, it's a virtual ground. So virtual ground requires negative feedback. Yeah, question. 아? 직각은 개인이 무한대라서 그래요. 개인이 유한하면은 요 블루 커브가 나오겠죠. 예? 그러면 얘들하고 만나는 점이 약간 바뀌어. Vx가 완전히 0이 안 되죠. 예? 파이니트 개인이 A가 되면. 그러니까 지금 뭐냐면은 이게 이 기울기로 말할 것 같으면 VO 나누기 VX잖아요. 그제? 그러니까 요 기울기가 VO 나누기 VX 이게 개인이라고 그냥 개인. 이거는 저 서프라이 볼티지. 여러분들이 플러스 마이너스 15V 서프라이를 쓰면은 얘는 한 플러스 마이너스 13V에 멈춰버리죠, 가다가. 그죠? 서프라이 없으면 계속 갈 텐데. Yeah, let's just see. Yeah, so this is for the case of finite gain. So, yeah, I equals 0 here. Yeah, I equals 0 there. But A is finite. So I have a finite gain, right? Finite gain. Then, see, yeah, Vi equals 0. Yeah, okay, everything is 0. Vx equals 0, Vo equals 0. Oh, that's fine. Good. How about the Vi positive? Yeah, in that case, see, my Vx is not 0, right? My Vx is not 0. Yeah, see, for that case, see, let's see. Yeah, I will use this one. Yeah. So here, see, this equation shows from here to there, my VO should be minus A Vx, right? Okay. Then I will substitute this one into here. See, then what's my Vx? So my Vx R1 plus R2 should be R1 VO. VO is minus A Vx plus R2 Vi, right? So my Vx happen to be what? Yeah. Oh, I will give anyway. See, this is A R1 plus R1 plus R2 Vi, right? Yeah, I will divide A here. See, this is if I divide A, what happens? Oh, I don't have A. Okay. Anyway, then what's my VO? Yeah, my VO. I will substitute this equation into there. Then my VO will be minus AR2 AR1 plus R1 plus R2 times VI, right? So I will divide A in both equations times 1 plus R1. Oh, so is it R1? R1 plus R2 AR1, right? So I have this much gain error, right? In the ideal equation, I have this equation. I have some gain error 1 over A, right? So my Vx is non-zero. Virtual ground doesn't work. My VA has some gain error this term. Gain error is, this is my gain error term, right? Yeah, that's my gain error. Yeah, question. No? 어? 어디? 어디가 R1이라고요? 여기는 R1이고, 어? 어디? 여기? 요거? 그러네. 맞지. Yeah, if you use a virtual ground approximation, you can get this equation, right? I have some gain error, right? 1 plus this term. Yeah. Question? No? Okay. So, see, if I have a positive feedback, what happens? Say I sent my output to the positive input node. Then there is no virtual ground. Okay? So again, my A is infinite, my current input is 0. So because current input is 0, the same Vx equation holds here. Alright? Then, see, what's my VO? Yeah. Where is it? Where am I? Computer. Oh yeah, I got it. So my VO equal what? Just R1, right? Yeah, R1, R1 plus R2 Vx minus R2 Vi, right? So I will plot again VO Vx curve here, depending on Vi. So if my Vi equals 0, if my Vi equals 0, it will be like that. I mean, this is my curve. Because see, the slope of V of X is only R1 plus R2 over, that's the slope of this curve. However, this gain curve is, see, because Vx is positive, negative input is 0, so this slope is A. A is much larger than this slope, right? So, anyway, if Vi equal positive, I will get this curve. So I have 3 operating points here. But if you look at it, this is a very unstable point. If there is some noise here, say for example, so those are stable points. If I have some noise in Vx, see I have some Vx increases a little bit, then VO increases much larger, then this larger increase will further increase this one further increase, finally explode, it doesn't stay there, right? Either this way, because Vx is increasing, it will go to this operating point very quickly. So I have 2 stable operating points, right? So, yeah, my Vx is no longer 0. So at this operating point, see, my VO should be around 13 volt if your VCC is 15 volt, okay? Yeah, in that case, my Vx is pretty large, right? I have a pretty large Vx there, right? This is no longer 0. Yeah, if I further increase Vi, then see, I have a single operating point, right? Then my VO is very large, right? It just remain there. So see, if I let's just say if I increase Vi, say I starting this Vi minus 13 volt, then this is my Vi, there is my VO. So if I start from here, very negative voltage of Vi, yeah, that Vi is the operating point is here, this is for Vi negative, right? So my output is this very negative voltage there. Then if I keep on increasing Vi, see, then until here, it will remain there, right? It will remain there. So it will remain there, and then it increases like that. And then if I reduce it in the opposite direction, so there is some hysteresis, right? Hysteresis. Okay, any question? No? No question? Yeah, op-amp circuits usually we use virtual ground. So here, see, negative feedback, right? We have to check it's a negative feedback, right? Negative feedback. Because VO is connected there. Yeah, in a positive input node, no VO is connected there, right? So virtual ground, virtual ground. virtual ground. Okay. So virtual ground means this voltage, if I have this voltage V3, the voltage should be the same, right? I know I equals 0. I equals 0. Yeah, so from V2, R1 and R2, I can easily calculate the V3 because the same current flows through R1 and R2 here. So that's R2. So I got this V2. I know same current flows through here too, right? I2, I2. Okay. So Yeah, I know I can calculate V3 because I equals 0 by using superposition principle. R1 plus R2, yeah, R1 times what? VO, R2 times V1, right? They should be the same, right? They should be the same. Then, how can I calculate it? Yeah, R1 VO plus R2 V1 should be same as R2 V2. So my VO should be R1 over R2 V1 minus V2. Okay? Yeah, this is the instrumentation amplifier. It's very powerful, so my input impedance is infinite. So I have two stages here. So I know this is a negative feedback, right? Negative feedback. So here, negative feedback. Negative feedback. Yeah, all negative feedback. So I have a virtual ground in all three op-amps. Okay? So I know this is V1 because of virtual ground there. I know this is V2 because of virtual ground of this op-amp, right? Then I know the current, the voltage drop across R1 is V1 minus V2. This same current must flow through there, right? So this V3, V4, V3, V4. Yeah, I can calculate easily V3, V4, right? Because say V3, V4, the voltage drop is 2R2 plus 1R1, right? R1 plus 2R2 times I. How about the V1 minus V2? That's R1 times I, right? So my V3, V4 equal V1 minus V2 R1 over R1 plus 2R2. Yeah, see, I don't know the each voltage, but I know the difference, right? I don't know the voltage of this one. Uh, yeah, actually, I cannot, I can calculate it because of this V1, okay? Anyway, we need just a difference, okay? How about the, yeah, this V3 can be easily calculated, R2I plus V1, right? Okay, anyway, I don't need that one in calculating VO. So what's this voltage? Yeah, this voltage is only, this is V5, this is V5, right? So this voltage is, yeah, you can find easily. This is R3, R4 times what? V4, V3, V4, right? So you will calculate it. R1, R1 plus 2R2, R3, R4. Is it negative? Yeah, this is negative, right? Negative. Okay, any question? No? Yeah, just review, right? A little bit more complex one. How come I have so many left? Oh yeah, this is a spice manual. So I think you can easily go there. Yeah, this is, I think this is, it belongs to lab 2. Oh, you already did, no, this is, did you do the op-amp experiment already? Just RLC. Yeah, you will get lab probably week 3 or something. Yeah, this is a filter, second order filter, low pass filter. Say, here see, you can see negative feedback, right? So this is a VO, so should be VO because of virtual ground, right? Then see, I want to calculate the transfer function uh, of VO with respect to VI. Okay. Then see how can I calculate that? Yeah, see, because this I equals 0, this I should be same as this I, right? So I can calculate this voltage easily because impedance divider, okay? So voltage drop between here and ground is just impedance ratio. Then I can apply KCL. Say, what's this voltage? This is, for example, I will say V3. This is V3. Yeah, I will apply KCL at this node. Then I can find the transfer function, right? The second order transfer, low pass filter. It should be, let me see. Yeah, at the DC, omega equals 0. Yeah, this is my DC, right? DC. Open circuit. This is open, open, open. What happens? Current is 0, current is 0, current is 0. Oh, this is VI, right? So at the DC, my VO is equal to VI. At the very high frequency, this is very high frequency. Very high frequency. Then capacitor is short circuit. Okay, if it's a short circuit, yeah, this voltage should be 0, right? Because the capacitor is short circuit, this voltage is 0. And then this is a short circuit. Oh yeah, it should be VO, right? Short circuit. Yeah, this is a 0. This is a VO. Actually, this 0 means this is 0, right? This is a VO. This is a VI. What happens? Let me see. Short circuit. Yeah, this is a short circuit. Oh, actually, so because of this short circuit, my VO is 0. See, because of this virtual ground, my VO equals 0. So this is a 0. There is shouldn't be any current in here. So this voltage is 0 because the current is 0. The voltage drop between there, because VI is different from there, it just flows in there, right? So no problem. VO equals 0. So you can figure out it's a low pass filter. You can calculate transfer function, something like that, right? Something like that. Or S for something. Question. Yeah. I가 어디로 갔냐면은 오피암프로 갔어. 그러니까 VI는 하고 여기는 0이니까 VO가 0이므로 얘가 VO인데 여기는 I가 0고 요게 이렇게 가가지고 이렇게 갔죠. 이렇게 가서 지금 오피암프가 파워 서플라이가 있을 거 아니에요, 그지? 그래서 그냥 오피암프 회로를 흘려버렸어. 그 KCL이래요. 그렇게 따져봐도 요 VI하고 이쪽 그라운드하고 얘가 이거 이렇게 흘러다녀. 오피암프 그 속으로 들어가 버렸어. Yeah, question. No? Yeah, there is a positive feedback here, right? Yeah, positive feedback. And then there is also a negative feedback. Yeah, it competes each other. So let's just see what happens. Yeah, for example, see, let's just see. It's an oscillator that what's the voltage V2? Where is voltage V2? I think this is V2, right? Yeah, V2 is, see, the current is 0 in op-amp input node, right? So Yeah, so it works like that. See, this V2 voltage, it's changing. It's changing minus 3.3 plus 3.3. This is the time axis. When it increases, say, let's just see, when this is what? This is 10 volt, huh? 10, 3.3. 10, oh, okay, this is 13.3 volt, okay? Yeah, at this state, my V6 was 13.3 volt, right? And this voltage is 3.3 volt, okay? So, because of this RC circuit, capacitor is keep on charging, it increases toward this voltage. When it reaches 3.3 volt, so this tries to be negative input tries to be larger than positive input. Then this V6 suddenly goes to minus 13.3 volt, and this voltage is suddenly changed to minus 3.3 volt, and then this tries to decreasing. When it reaches here, the opposite operation occurs, and it keep on oscillating. Okay. So you can calculate this T1, T2. For this T1, this waveform is what? Initial condition. And initial condition is here. Final value is what? 13.3 volt. Okay, that's the final. This is initial. Then let's see. Yeah. So that voltage is let's see. You can see final minus initial times exponential minus t over RC plus final. Okay, that's the wave equation here. Okay, this is final, initial, final. Okay. Oh, it's just slightly wrong, right? This equals 0. Oh, the other way around. The other way around, right? So if t equals 0, I will get this initial value. If t equals infinite, I must get this final value, right? So this equals t equals 0. T equals 0. 3.3. Okay. Then when it reaches 3.3, that should be my T1, right? This is T1. Okay. So you can calculate T1, T2, and then my period is oscillation period is just this one. Yeah. Question. Yeah. 그게 이게 15V를 걸면은 서프라이를 플러스 마이너스 15V 741 OPMP에 걸면 이 OPMP가 그 정도 올라가요. 이 부근에 올라가. 한 13V 부근에 올라가. 그래서 그걸 계산 쉽게 하라고 지금 CK 3.3K를 해놨는데 13.3이라 가져간 거예요. 뿔로 못 올라가. 뭔가 몇 개 가려가지고. 여러분. 예. 오실레이션 주기 구하려고. T1, T2를 알아야 오실레이션 피리어드가 나오잖아요. 열심히 구했지. 보통, 요 회로에서, 여기 13. 얘가 13.3이 됐다가, 마이너스 13.3이 됐다가 그러고 있잖아요. 그죠? 그러면 얘가 우선 13.3이면은 이 캐패시터 볼티지는 바이너리는 가만 놔두면 13.3으로 갈 거 아니야. 초기 조건이 지금 마이너스 3.3인데, 그래, 초기 조건, 이니쇼, 여기, 파이널, 싱글 타임 콘스턴트니까 이렇게 쓰면 돼요. 파이널, 그래서 싱글 타임 콘스턴트니까 내가 어떤 상수 플러스 상수 익스포넨셜 마이너스 t 오버 rc라는 걸 알아요. 예? 그죠? 그럼 초기 조건 파이널 컨디션을 이렇게 초기 조건 빼기 파이널 컨디션 하면은 이거 파이널 컨디션 t 이퀄 0 같으면은 i만 남아야 되잖아. 초기 조건만 남아야 되잖아. t 이퀄 0. t 이퀄 뭐한데? 파이널만 남아야 되잖아. 그죠? 그렇죠. 얘가 V2죠. V2. 그래서 얘가 이제 나중에 얘가 13.3을 유지하니까 얘가 3.3으로 됐으니까 얘보다 커져 버리면은 이게 뒤집어져 버리죠. 그때까지 시간을 보하는 거잖아요. 얘가 3.3 될 때까지 시간. 그게 P1. 오케이. Yeah, surprise. You need a hand analysis, right? So I think this is some diode circuit. So yeah, voltage source. This is DC voltage source. Node number DC5. This is a pulse waveform. Node number DC0. Pulse 0 to 5. Delay time, rise time, fall time, pulse period. This is high period, high time. This is a period, right? Some sine wave, sine wave. If you put sine wave 0, 5, this is 0 plus 5 sine 2 pi 1000. So there is no delay, something like that. This is 1 kilohertz sine wave, amplitude 5. DC analysis, operating point DC analysis, transient analysis, AC analysis. What's this thing? Resistor, right? Inductor, diode, BJT, MOSFET. Yeah, this is dependent sources, right? Dependent sources. Yeah, dependent sources. Dependent sources models the physics of active devices. Yeah, voltage control voltage source. This is a voltage control current source, okay? You can see those starts with E. Okay, question. So we have additional homework number 1, which is 14. And then today, 8 p.m., discussion. Okay, yeah, let's start here.